Alright, today's lesson is on impulse. So if we want to change momentum, of something, then we need to do something. So essentially though, what do we need to do? We need to apply a force. Alright, so speed it up, slow it down, change its direction, we need to apply a force involved in that. So normally when we would do that, the force that we would apply might be of short duration. Alright, and so that's where we get the idea of impulse comes into it. So the impulse is a force of short duration, or the impulsive force. So there you go, impulsive force. Alright, so we'll term it impulsive force. So by definition, the average impulsive force, is defined as the change in the momentum with time. Alright, so in your notes, i.e. change in momentum in time. So another way, of course, we can write that is that it's the final momentum minus the initial momentum over the time it took. So the definition then of impulse rather than impulsive force, so this here, this force average, that's the impulsive force that we're talking about. But impulse itself is equal to the change in momentum. Alright, so change in momentum, so the impulse I equals delta P. Now, if we come back to this over here, and looking at this one, then the change in the momentum, if we times both sides by time, then the change in momentum, which is the impulse, would be the average force by the time. Now, how we normally often see this is maybe F av, maybe not the av, but F delta T. And again, the units for this, again, not much thought's gone into this to be very creative. We go Newton and second the units of each of those. Alright, so we've got a couple of concepts here that if momentum changes, we say that there's been an impulse. And the other thing back here is that the average, this one here, that the average force, or the impulsive force, that's the force that caused the change in the momentum, is the change in momentum over the time. Alright, let's have a look at an example. Alright, so here's an example. Change in momentum. When served, the tennis ball leaves the racket at force speed of 45 metres per second. The impact time between the racket and the ball is 5 by 10 to the minus 3 seconds. And the mass of the ball is 0.06 kilograms. Find the average impulsive force that acts on the ball. Alright, so what do we know? Well, what we know from before is that our average impulsive force is the change in momentum over the time. Now, in the information up here, we've got the time. The time is 5 by 10 to the minus 3 seconds. So it'd be good to have the change in momentum. All right, so got a couple other bits of information. Speed before being hit is 0, and it gets hit at and leaves the racket at 45 metres per second. So our initial momentum, which is m times u if you like, initial speed, is 0.06 times 0, which of course is 0. Our final momentum, which is the mass times its speed after it's been hit, so 0.06 times 45, and we do 0.06 times 45, and we find that comes out to 2.7. So our change in momentum then is our final minus our initial, which is 2.7 times what am I talking about? 2.7 minus 0, which of course is just 2.7. So my average impulsive force would be 2.7, not 2.4 as I've written down there. Would be 2.7 over 5 by 10 to the minus 3. Stick that in your calculator and you get 540. Of course, it's a force, so 540 Newton was how hard, the average, I should say, the average force that was applied to the ball by the racket. Now, talk to you about average forces. So, really, the force is actually going to change. It's not likely to be constant. You know, at 540, it's going to change, be less than that when the ball hits the racket. So here's the racket and there's the ball. Just as the ball touches, there's a little bit of force, but then when the racket is bending and the ball's in there, there's going to be more force, and so the ball's going that way, and then the racket's going to force the ball out, so it's going to go, and it's now moving that way, and then it's going to go back to here. So in each of these, the force acting on the ball by the racket's actually going to change. So what we really need to do is we need to look at force time graphs. They're the things that are really going to be useful to us. Why are they going to be useful to us? Well, remember that impulse is force, average, and the time. So if we have a force time graph, we've got these two things, so we should be able to find the impulse. All right, so here's a force time graph. So we've got net force here, we've got the time here to find the area here, and you know we know that simply area. Some basic stuff. If I just look at this square bit here, we're just going to go length by width. Now the length and the width are force and time. So force times time, remember, is impulse. So the area under a force time graph is impulse. So the reality, when the force actually changes, we need to look at a force time graph, and because we know there that the area, impulse is the area under a force time graph. All right, so how do we actually use these? Well, one example of how we use these would be airbags. So airbags work like that because remember that the average force is the change in momentum with time. So if we're in a car or something, the momentum, we're moving 60 km/h, there's a momentum, there's a momentum. This time bit here, we can change this, because if our time increases, because what that means is the force is going to decrease. Alright, for the same change in momentum, which of course is impulse. Now, that's what airbags do. So instead of whacking your head on the dashboard and stopping very quickly, your head goes into airbag and stops more slowly. So the force on your head is less, and therefore you survive instead of. Alright, so here's another example. So, for example, a skier. So if you're a skier, for example, and you fall over, whatever speed you're going, but you fall over and you just slide along the snow. You're going to slide along the snow for, a period of time. And in this case, the area is an impulse of 300 Newton per second. So you're going to, slide over there for a period of time. Low force, as you can see there, 45. Now, compare that to, say, when you run into a tree, for example. So you run into a tree, you're going to stop very quickly, and but if you've still got the same impulse or the same change in momentum occurs, for that to still remain at 300, then what you've got to have is a large force, a force of 6,000 Newton, according to this example here. And so then that's probably not going to be good to your body. 75 Newton, you're going to be okay. 6,000 Newton, possibly not. It's going to hurt. All right, so things like airbags, helmets, all those sorts of things, what they do is they try and increase our time. So we want time up so that the force goes down. All right. So text questions. So there's some text questions there that you've got, and then again a whole stack of past exam type questions. Again, you should be selective with those and save some for later.